Okay, this is the third video on NetworkX. So again, in the starters folder, let's click on this Roads instance, or this Roads notebook. Okay, so again, we're going to be working with NetworkX, and we're again going to be calculating distances, but we're going to solve this shortest path problem for a very large instance. So the instance I showed you earlier was a kind of a toy instance with just a handful of nodes and edges. But we're going to consider an actual road network that has about 500,000 nodes and over 1 million edges. So this instance is actually coming from this Dymax challenge, specifically the 9th one that was about shortest paths, or the shortest path problem. So this was, I think, back in 2005, 2006, something like that. And the particular instance that I'm using is this one. It's for Colorado. And you'll see here that you can download actually two different graphs. One of them is for the distances. So we have, let's say, miles on the arcs. That would be the attribute. And there's also one for travel time. And so actually, I downloaded the travel time instance. So it's not too big. So 5 megabytes. If you got the full road network for the US, it's going to have 24 million nodes and 58 million edges. And I think this is what, like a third of a gig. So I think when you unzip this, it might be closer to a half gig. So this one's quite large. Okay. So anyway, in our this code that you downloaded, this road network for Colorado should be here somewhere. Let's see. Oh, maybe I didn't upload it. Okay, so you'll have to download this yourself, I believe. So you'll need to go to this Dymax website. You'll need to download this Colorado instance, and you'll need to unzip it. Okay. Then after you unzip it, I think, let's see, maybe I need to, I'll add it myself. Give me 1 second. Okay. So I pasted that file. So the USA Road Network, T I think is for travel time, COL is for Colorado, and GR I think is for graph. Okay, so we're going to read in this network. So maybe I'll go ahead and copy that file name. Okay. So here's what the text of that file looks like. So each row has a single character at the beginning. So C is for a comment line. P is for, I think, problem. So this is a SP shortest path instance. This is the number of nodes. This is the number of edges. We have a couple more comment lines. And then I think all of the other lines in this file, or other rows in this file, are arc lines. So it specifies the head of an arc, the tail of an arc, and the length, or I guess the travel time of this arc. Okay, so I've helped you out. I went ahead and gave you this function that will read that file and save it as a NetworkX file, or NetworkX graph. Okay, so we'll just run that cell, so we'll have that function at our disposal. Okay, so the file name that I'm trying to read is this, which I had copied pasted from earlier, and let me put that in quotes. Make sure it's a string. Okay, so then I'll read in this file using that function from above. So this will read the file and then return this graph G. And I call it G because this is actually an undirected graph. Arguably when you're working with road networks, you should have, let's say, travel times going in either direction because they may be different. But for whatever reason, for this Dymax implementation challenge, they've used undirected. So I think all of these US road networks have been given as undirected. Okay, so that'll be fine. Okay, so let's read it in. This may take a couple seconds, not too much. It is a decently large file with 1 million edges. Okay, so the expected number of nodes was that, according to the problem line of the file. That. Then we have this number of expected edges. But for whatever reason, the number of actual edges is different. And I think that may have something to do with the directed versus undirected nature of the graph. So I'm reading it in as an undirected graph. And so each one of these edges will be counted once, but maybe this expected number of edges in the problem line, maybe this was for, they counted each direction of the edge separately. And I think it doesn't quite add up. This is not quite, it's not exactly equal to twice this number. So there may be some other issue with this file, but at least in my experience, we can still use it. Okay, so let's calculate the, let's say the shortest path or shortest, let's say travel time from node 1 to every other node. Of course, it doesn't have to be node 1 that we start from, but it's easy. Okay, so we want the shortest path length in our graph. We're starting at node 1. And then now we have to specify what weight are we using. And since this is a, this network stores the travel time across each edge, I've actually chosen to store these times in this time attribute. So it's no longer a weight attribute, it's a time attribute. So here, this weight that I'm using for computing shortest paths, I need to refer to the time. Okay, so this will return that distance dictionary, or I guess time dictionary in our case, so I'll call it time. And you'll see that Dijkstra runs in just maybe 1 second or less. Dijkstra's algorithm is very quick, even for this node with 1 million edges. Okay, so this graph has, close to 500,000 nodes. So if I were to print out this entire time dictionary, it would take up a lot of space and a lot of time. So I'm just going to print the times to the closest or the nearest 20 nodes. So I'll pick 20 nodes. And so far I've printed 0 of them. So for nodes I and time.keys, I guess first I'll check if the number of nodes and their times that I printed so far is more than that 20 that I want to print. Then I'll go ahead and break this for loop. Otherwise, I'll go ahead and print the time to, let's say, time from node 1 to node I is time to I. And then I'll just want to make sure that I increment the counter for the number of nodes that are printed so that this will eventually stop this loop from continuing on for 500,000 nodes. I print the 20 closest nodes. That does it. So this was just to illustrate that you can use you can apply NetworkX and apply Dijkstra's algorithm for very, very large graphs. I think that the time to run Dijkstra is actually smaller or less than the time to read the graph from the file. Now, if you're working with if you're actually using this in an application, I think you would need to get these road networks from another source. So I know that there's something called OSMNX. So I'm not going to discuss this in this class, but if you are out in industry and you do need to get this road network or travel time network, you might consider using this Python package. So it uses OpenStreetMap to get these road networks. And I think if you spend a little time Googling, you can find some tutorials for using this package. Okay, that does it for these introductory NetworkX examples.